Unifying classical and quantum physics. How classical and quantum physics can pass smoothly back and forth. Here is the simplicity of current physics. Hamiltonians can serve as good examples, such as classical Hamiltonians, p squared plus q squared over 2 plus g times q to the 8th power, or quantum capital P squared, capital Q squared divided by 2, and g capital Q to the 8th power. Or even classical Hamiltonian pi squared, phi squared over 2, and g times phi of x to the power 8, all integrated dx, and then is quantum Hamiltonian pi hat of x squared and phi hat of x squared over 2 plus g times phi hat of x to the power 8 dx. When zero can become a quantum issue, wave functions love to calm down Hamiltonians, and here they are. The Hamiltonian would be very, very big if we were integrating over the fields themselves. However, they can be controlled by the wave functions in this structure equal to 1, and they run from plus to minus infinity, including this 0 with them. Now, there's a second thing to think about. We have a momentum squared and a new term here, 2h bar squared divided by phi of x squared, and the rest is the same. But this can be difficult if that was 0, so that can't be 0, and that's the way it's arranged here in the wave functions and putting it here. And that is indeed not equal to 0, although it runs for otherwise from plus to minus infinity. And now we have a giant leap in quantum physics. Canonical quantization, CQ, requires a little q between minus and plus infinity, or for fields, phi of x, between minus infinity and plus infinity. But affine quantization with an AQ opens a gate only to retain space. That means that Q is positive, Q is everything except 0, Q squared is less than B squared, or Q squared is greater than B squared, etc., etc. Well, now we have, in this situation too, we have the field magnitude here between 0 and infinity, but it does not reach 0. And that's very clear here. Phi of x is not equal to 0 because that can cause difficulties. This story is welcome. The quantization of many problems fails. For example, h equal into pi of x squared plus gradient of phi of x squared plus m squared times phi of x squared all over 2, and plus g times phi of x to the power 4, integrated over 3 spatial dimensions. If we take this out here and put it not down here, that's even worse than that. This classical Hamiltonian is going to be difficult more than this one is for quantization. The problem lies with canonical quantization. Valid solutions require affine quantization, which only needs a simple, small term. Here it is, 2h bar squared divided by 5x squared. Just put it next to the family of the pi hat squared. Here's a simple question. Suppose your classical Hamiltonian reads this way. H equals pi of x squared plus m squared phi of x squared all over 2 plus a potential of phi of x integrated with s dimensions and with various potentials such as v of cap x squared, cap x 100, 1,000, x to the minus 2, x to the minus 100, and 10 to the minus 50 times x to the minus 100. Along with others, this can be accepted. Why do we ignore v of phi of x equal to h bar squared divided by phi of x squared? That's something we should not do. Here's a brief introduction to affine quantization. I have the line up here where for canonical quantization, Q has to run between minus and plus infinity, and that's the line. And here we're going to chop it off at Q equals 0 and just take the positive Q, here that's this line. Now the momentum can go from plus to minus infinity, but now we have arranged it so that the Q is strictly positive. That forces the momentum and the other momentum, they are not self-adjoint together. Here is the new term D equal to P times Q, and we have Q positive. And now the dilation operator is cap P dagger Q plus Q P dagger divide by 2 is self-adjoint, and Q is Q self-adjoint, and as well it is positive. Now, while P dagger is not equal to P, it does follow that P dagger times Q will equal cap P times Q. Now the kinetic term, which is P squared, is now in these variables D squared divided by Q squared. And promoting that to operators becomes D cap Q to the minus 2 times cap D. And indeed, that unravels to itself to cap P squared plus 3/4 h bar squared over Q squared. This extra term created, if you like, from the P kinetic term here, goes to Q equals 0, just like our situation here. If that was Q plus B up here, this would be Q plus B down here. And it acts like affine quantization knows where the space ends because it has created here, and Q going to 0 is the end of space in this picture. Now the half harmonic oscillator here is the Hamiltonian classical p squared plus q squared over 2, and we have enforced that q is strictly positive. Here is the quantum situation for this, which we have talked about before. Now we're putting on extra terms here. Indeed, the eigenvalues for this very equation are 2h bar n plus 1 for n equals 0, 1, 2, 3, etc. And that compares with the full harmonic oscillator eigenvalues, which are h bar times n plus 1/2 for n over there. It's almost like this little 2 was taken there and put here. There is clearly a valid connection in these equations right here. Note the harmonic oscillators up here. Here is the full Q between minus and plus infinity. That's the classical Hamiltonian. And here is the quantum Hamiltonian here. And these are the connected eigenvalues, h bar times n plus 1/2. And that's n 0, 1, 2, etc. And these are equal spacing. Now, here is the situation when Q is strictly positive. The classical formulation is still the same, and here, in fact, is now the new quantum function where we pick up this extra term because Q is only positive, and indeed that has eigenvalues which are slightly different, 2 h bar times n plus 1, and they are again equal spaced. In fact, if you moved q to q plus b, and then you would find down here, it would look like here, and that again equal spacing, and if b went to infinity, it would move back into this story right up here. Half harmonic oscillator here, and its h bar potential. Now this is the standard and old formulation of classical things, and this has a Q positive, which is certainly there in the quantum theory of this business, but we could also should be in the new formulation should include this as a potential because when Q is tiny, it's very, very large, and this belongs there. And the eigenvalues for this equation are simply 2h bar times n plus 1, while the full harmonic oscillator eigenvalues are here, h bar times n plus 1/2, and these are equal spacing stories, and clearly there is a valid connection. An example of careful applications. Here is the classical theory for that, and here is the quantum Hamiltonian for that. Integration values stay the same if phi of x not equal 0 and phi hat of x not 0. Nothing will change these integrations, which allows us to put a classical Hamiltonian in here. This is a potential in which when phi of x gets very tiny, it is very, very, very strong, and that leads us to the quantum Hamiltonian down here, and then we get our valid results. a preparation for more. Let kappa of x equal pi of x times phi of x, in which phi of x not equal to 0. For this equation of the classicals, kappa of x squared divide by phi of x squared plus m squared times phi of x squared all over 2 plus g times phi of x to the power p, integrated over s spatial dimensions. In order to represent pi of x correctly, then phi of x has to live in magnitude between 0 and infinity, and kappa has to be there between 0 or equal to 0 and infinity. And incidentally now, this requires that 0 less than magnitude of phi of x to the power p less than infinity for every one of these, for all of them, p running from 0 to infinity. Now for some interesting scaling. Here is the commutator for this at the same point, x equal x here, and that becomes h bar times delta of L of 0 to the power s, and that equals infinity. And this is not infinity yet. We will make it infinity later, but right now is for h bar times cap w is very large. The phi of x is not 0. Kappa hat of x made by pi hat of x dagger, phi of x, and phi of x times pi of hat over 2. Pi of x squared, which is now kappa of x squared, divided by phi of x squared, is promoted to the operators kappa hat of x times phi of x to the minus 2 times kappa hat of x, and unravel that, it becomes pi of hat x squared plus 2 times h bar squared, and directs delta of 0 to the power 2s divided by phi of x squared, but this is an infinity here, and we have to deal with that. Kappa hat phi of minus 2 kappa of hat unravels to pi of at squared plus b h bar squared cap w squared divide by phi of x, phi squared, pi hat squared and phi squared, and multiply that by w and in times phi hat squared and phi squared together. That means in the canonical term, we had added the w here, we've added the w here, and at that way, we have got a single w here, so let's multiply with w to the minus 1, and what comes out of that is pi hat of x squared plus b h bar squared divide by phi of x squared, and we have b to our play thing with between 0 and infinity. And now if we want to do this, we can send W to infinity now. This is a very important analysis. We've arranged that phi hat of x equals phi of x not equal to 0. Kappa hat of x equals pi hat of x dagger phi of x plus phi of x and pi hat of x all over 2. Now here is the quantum Hamiltonian that we get from this. Kappa hat of x, phi of x to the minus 2, kappa hat of x plus m squared times phi of x squared all over 2 plus g times phi of x to the power 4 d for s dimensions, spatial dimensions. Now using scaling, we will choose b equal to 2 so that our quantum Hamiltonian now reads pi hat of x squared plus 2 h bar squared divided by phi of x squared plus m squared times phi of x squared all over 2 plus g times phi of x to the power 4 and integrated over s dimensions. A valid result that has been proved to be correct by Monte Carlo in using h bar equal to 1 for help in that. Note, pi hat of x squared plus 2h bar squared divided by phi of x squared, acting on the integral of phi of y squared dy equals 0. Here is a familiar example. Phi to the power 4 and to 4 space-time dimensions. A canonical quantization for this classical Hamiltonian, and the canonical quantization is this quantum Hamiltonian down here, where Schrodinger's representation can let these be the same, and this becomes the operator. And of course, we now know that turned out that G acts like it was 0. It didn't do anything for the quantum theory. But now an affine quantization for this problem with the extra magic term here as a classical story, and now put it in here in the quantum story here, and it turns out that G is acting as it should. Now here is a royal road to absolute success. Backed by affine quantization, we have found that a standard canonical quantization plus the new magic term 2h bar squared divided by phi of x squared leads to absolutely valid results. Since the h bar term arose from the kinetic factor, the new term is placed in this positions pi hat of x squared plus 2 h bar squared divided by phi of x squared. Here is a grand summary. Our focus on zero has been on present or absent, which was designed to include terms like phi of x to the minus 2 power, which then requires that 0 less than absolute phi of x less than infinity. It's not equaling to 0. Throughout all the equations, then so have the Hamiltonian, which is pi squared plus 2 h bar squared divided by phi of x squared plus m squared times phi of x squared all over 2 plus g times phi of x to the power p for s spatial dimensions integrated. And the quantum operators for that is the Schrödinger representation, pi hat of squared plus 2 h bar squared over phi of x squared, m squared times phi of x squared all over 2, plus g times phi of x to the power p and s spatial dimensions, in order that the magic term is well included. And note that p can be 4, 6, 8, anything you like that's even. They are well accepted. Here are some references for the problem. An affine quantization for beginners could be here. If you like, an ultra-local field and an ultra-local gravity, which are simply taking off the spatial derivatives, are done here. We have standard fields done here, and now corrected from this as well as possible. We also have Einstein's gravity done on the archive term. And finally, YouTube has a performance about why the number 0 was banned for 1,500 years.